So yesterday we are going to be learn the new concept and new things. So your next article, we will see. So next is the work done during the longitudinal strain. So we know that is the body in a natural shape, then it possesses the minimum potential energy. Any object in the universe will always acquire the minimum potential energy. But when you apply the external forces, deformation is a take place, and then the deformation take place is nothing but the molecule displaced from its original position. Means there is the intermolecular distance will be changed. Once the intermolecular distance changes, then there is a restoring force will be introduced, and the restoring force starts to be act so as in the opposite direction of the external applied force, and it always try to take its original shape of the body. Now we consider the work done during the deformation, which is stored in the form of the potential energy. Means when the body is a deformation is take place due to applied force, so there is an work is done, and that work is stored in the body is the form of the restoring force, and it's called as the potential energy. So potential energy is increases when the body is in deformation. So that energy is called as elastic energy, or it is called as also strain energy. So in the elasticity, there are the three type of the strain. One is an longitudinal strain, volume strain, and the shearing strain. So we'll be study the work done for the every strain. So first is the longitudinal strain. So to study the work done during the longitudinal strain, we consider first L is the length of suppose the wire. So one end of the wire is fixed to the rigid support, and other end is an free ends where you apply the force in a downward direction. So suppose F is an our applied force at a free end, and L is an our original length of that wire. Suppose A is an cross-sectional area of the wire. Due to this applied force, suppose that an X is an increase in the length. So according to the definition of the Young's modulus is nothing but the ratio of the longitudinal stress to the longitudinal strain. So we got the Y is equal to stress upon strain. So this stress is nothing but the force per unit area, that is applied force per unit area, that is equal to F upon A, and strain is nothing but change in the length to the original length. So increase in the length is an X, and your original length is L. So X upon L is an equal to strain, and stress is a force per unit area. So by using this, so we got the F is equal to, it can be only the rearranging term. So we got the, this is nothing but F upon L, F into L divided by A into X. So from this equation we can derive the F is equal to, so move AX to left sides and then divided by L. So we got the AX divided by L into Y. So we got this equation. Now this is the force which you have to apply the external force. This force is an at equilibrium, it is equal to the restoring force. Now this force, there is an extension is suppose the dx. So if there is a small displacement, that is small change in the length of the wire, suppose the dx, then we got the basic, that is the work done formula. That is the fundamental formula, is the work done is equal to force into displacement. So force is nothing but Ay divided by L into X. That is an earlier equation, that is Ay divided by L into X. This value you have to put in this equation. So you got this equation. Now this is an work done when body is stretched through the distance dx. Now suppose that our body will be stretched from the 0 to the L, that is the small L is nothing but the increase in the length. So total work done by the external force is equal to this. Work done is equal to 0 to L, F into dx. F into dx, F is nothing but AY divided by L. Now, A is the cross-sectional area of the wire. A is the cross-sectional area of the wire. So, cross-sectional area of the wire, suppose the constant for the small applied force. And Y is an X modulus. This much is depends upon the material properties. So, it is a constant suppose. L is the length of the wire is constant. So, you have to take the only there is the X, increase in length. So, you have to take an inside X only. So, you take the integration of the X into dx. So, we got the X square upon 2. Let's see, we got our first this Y into A. Y into A divided by L, and that integration value is X square upon 2. So integration limit is 0 to the L. So if you have to put the integration limit, so we got the YA divided by L is constant, so there is a 1/2. X is equal to L, so we got the L square. X is equal to 0, so next term is a 0. So we got the YA divided by L into L square divided by 2. So here, this is work done is nothing but this is L. So we got the L square, YA L square divided by twice M. Now this is the work done during the longitudinal strain. Now suppose this work done is stored in the form of the energy in the body, so it is called elastic potential energy. So we determine the elastic potential energy per unit volume. So we got this U is equal to this AY divided by twice L into L square. This is the potential energy. This work done stored in the form of the potential energy, so we got this equation. So if you want the work done per unit volume, then we can be determined, but before there, we consider U, that is the potential energy, elastic potential energy, 1/2 AY divided by L. Now this L square is written as L into L. So if you observe this AY divided by L, capital L into L is nothing but your the force. So this is called as the stretching force or your applied external force. So you got the potential is equal to the 1/2 into stretching force into this is the L. L is an extension, that is increase in the length. Yeah. So you got 1/2 into stretching force into the extension. So this equation can be written in the form of this 1/2, then the Y. See here, L divided by L, this equation can be written L divided by L, L divided by L. There is L is and one more. It can be divided by L, so multiply the L. So here write the L, multiply extra L. So there is L. This is your earlier L. So we got the 1/2 Y L upon L into L upon L AL. Now we have to observe your wire. So it is an your suppose the length L, and this is cross-sectional area. So if you have to take the product of the A into L, so we got the volume of this wire. So it is nothing but your volume. So if you want the work done per unit volume, so it can be nothing but it can be divided by AL here. So this AL will be the cancel. So this AL will be cancelled. So this AL is the cancel, so you got the 1/2 YL divided by L is nothing but your stress. YL divided by L is nothing but stress. L upon L is an your the strain. That is change in the length to the original length, so you got the strain. And Y into L divided by L is nothing but the stress. If you have to see the your earlier slide, so we see there is a stress is equal to Y into strain. So we got this stress is equal to stress is equal to y into strain. So we get the y into strain is nothing but L divided by L. So we got this y into L divided by L. So this is about the work done during the longitudinal strain. Now we consider the work done during the volume strain. So it should be remember volume strain. So we can consider this is nothing but the bulk modulus. So for that purpose we consider this is an cube. You have to suppose here is a force is applied tangentially in a downward direction on the upper face of the cube. Suppose you have the P and pressure applied. This is nothing but P. So P and force is related to each other. P is equal to force per unit area. So suppose your pressure is applied normally over the area A of the body. Volume of this cube original is an V. So volume of the body is this. So due to this applied force pressure, that is volume is decreased by the C, that is small v. So according to the bulk modulus definition, bulk modulus K is equal to P divided by V divided by V. That is the P is your stress. P is nothing but stress. That is called as volume stress divided by volume strain. Volume strain is a change in the volume to the original value. So we got this, we have to manipulate over the term. So we got the K into the P into V divided by V. If you are writing this equation for the P, so we got the P is equal to, this is multiply here, so this is divide, so KV divided by capital V. Now this is on your pressure exerted on your the face of the cube. Now suppose there is a small displacement dx. This is a small displacement of the dx due to your applied force. So there is a work done due to this applied force is nothing but the product of this two terms. So force is nothing but your P into A. So P into A. So you write here P into A into dx. A into dx. See here, this is an dx and this is a cross-sectional area. So we got the one slit. So this slit is nothing but, see here, this is an your slit. So this is an your change in the value. This is nothing but the change in the value. So this is the A and this is a dx. So product of this is nothing but the dv. That is change in the value. So we got there dv. Okay. So we got the P into dv. A dx is an your increase in the value. That is equal to the dv. That is equal to the dv. So if there is an increase or decrease the volume from 0 to the v, then total work done we can be determined by taking the integration of the above equation. So integration of these equations, we got the total work done. So you take the integration from 0 to the v, so P into dv. So P from your first equation, that is P is equal to kV divided by V. So if you have to put in this equation, we got the kV divided by V. Now K is a bulk modulus. It is a constant for corresponding material. C is an your original value, so it is constant. You take outside, so 0 to the V, V into dv. So if you take the integration of the x dx, that is x square upon 2, that is your v. So we get the v square upon 2. See here, v square upon 2 is an your integration limit. So if you have to write the 0 to the v, so if you write there in this equation, we got the v square upon 2 minus 0. So it is v square upon 2. So we got the v square upon 2. Multiply this constant k upon v. Now this v you can be written as like this, v into v. So you got the v into v. If you have observed the kv, kv is small, kv upon capital V, so we got the pv. It is the pv. So here is p, there are applied pressure, there is a v upon 2. So you have to put here 1/2 p into v. There is a work done, this is 1/2 into stress into change in the value. So this is work done. It can be the store in the body in the form of the energy. So it can be determined the work done per unit volume. Work done per unit volume. So it should be work done per unit volume. This is not the energy stored per unit volume. So we got the 1 half P into V only divided by the capital P here. So you got this equation 1 half P into V divided by V. If you are written here 1 half 2 1 upon 2 into P is nothing but your stress into C divided by V is the volume strain. So we got the 1 half into stress into strain. So this is an work done during the volume strain. That is you have to see there is a volume strain or the bulk more or less it is same thing. So should we remember this work done? So work done during the longitudinal strain or work done during the volume strain. There is one more work done or during the shearing strain will be seen in the next lecture along with your Poisson ratio. So this is on our students. You should be remember work done during the longitudinal strain and work done during the volume strain. In longitudinal strain, you should be remember this formula of the Young's modulus. Then you should be right only the manipulate. This equation is written for the F. So we got the work done is equal to force into displacement. Then force into displacement is a basic equation. It is used for the total work done. Only total work done. So we got this equation potential energy per unit volume or work done per unit volume okay. Then we got the work done per unit volume, that is your energy. So we got the 1 half into stress into strain. So each and every work done for the strain is and last equation is same for our R. So 1 half into stress into strain. In case of the longitudinal strain, we can replace the strain by the longitudinal strain and strain is by the longitudinal strain. And for the volume, it is a volume stress and volume strain. So it is a C work done. It is same thing, that is the bulk modulus basic formula. We can use this. It is a written for the P. So can be P is converted into the F. So that's why you should be remember the relation between the pressure and force. If you know, then it is easy to be the solve. Otherwise there is a difficulty. But you should be the remember this equation. So we got this dV. dV is an increase in the volume or change in the volume. So you can be determine the work done by the integration. So we got the total work done. And last equation is 1 half into stress into strain. So this is an about your the today's work done during the longitudinal strain and volume strain. So you should be the study it or read it. Thank you.